Okay, so I think we will go and do some properties of conditional probability. So, we did properties of probability measure. I probably listed some 7 or 8 properties, right. So, see, this is a valid probability measure on omega f, right. So, any property satisfied by probability measures is satisfied by this guy also. Probability of a dot given b satisfies all those properties, because it is a valid probability measure, alright. So, we will put down a few which are more specific. Okay. I have 3 actually. One, let B I let us say I equals 1 2 dot 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 be a partition of omega. So, what does that mean? So, it just means that so I E, it just means union B I equal to omega and B I intersection B j equal to null for I is not equal to j, right. And let A be some event. So, these are also F measurable. Suppose P of B I is greater than 0 for all I. Okay. Then probability of A is equal to sum over I equals 1 through infinity probability of A given B I times probability of B I. Okay. So, this is the law. So, this law has a name. You know what name it is? Total probability, the law of total probability, right. So, we are looking at a partition of the sample space by F measurable sets. So, BI's are F measurable and they form a partition of omega, and A is any F measurable set. Then you can write the probability of A as the probability of A conditioned on B times probability of B sum over all these partitions. Okay. So, in particular there is a very particular version of this which is quite useful. So, if B is any event with positive probability, B and B complement always partition the sample space, right, very trivial to show. So, therefore, you can write, so if in particular if B is in F such that probability of B is greater than 0, but less than 1. Okay. So, I am saying 0 less than PB less than 1. Okay. Then probability of A is of course your any F measurable set, it can be written as probability of A given B times probability of B plus probability of A given B complement times probability of B complement. Okay. This is a corollary of this total probability law, because B and B complement partition the sample space, and I have, so I can condition on this because B has positive probability, and I can condition on B complement also because B does not have probability equal to 1, it has strictly less than 1. So, probability of B complement is strictly positive. Okay. So, here I need both. Okay. So, how do you prove the law of total probability? This is, so this is equal to probability of A intersection B I, right. So, the RHS, so if you want to prove this, here the RHS proof, see if you consider this probability expression, this probability of A given B I is probability of A intersection B I over probability of B I. So, it will cancel this out. So, you will have RHS is equal to sum over I equals 1 through infinity probability A intersection B I, right. Now, B I's are disjoint, right. So, A intersection B I's are also disjoint. So, by countable additivity of P, I have this guy, this I can write as probability of union A intersection B I, agreed. Now, again I use this rule, right, the set theoretic identity, which says this will be equal to probability of A intersection union B I. But union B I is equal to well, yeah. So, this is equal to this is omega, correct, this guy is omega. So, I have A intersection omega, which is A, that is all. Okay. Oh, sorry, probability of this is A intersection omega, this is probability of A, correct, which is what I want. Any questions? So, this has so a typical example of the law of total probability is when you have these balls and urns experiments, right. So, let us say you have n urns, okay, and each of them has let us say urn I has ni red balls and mi blue balls or something, and you are looking at, so you pick an urn at random and then you pick a ball at random, okay, with let us say uniform probability. Then you can talk about, so you know that the probability of choosing the ith urn is whatever 1 over n in that case, and probability that you choose a red ball given that you chose a particular urn I is ni over ni plus mi. So, you can calculate the unconditional probability of picking a red ball, right. So, that is the kind of law this is saying, right. So, you first condition on what urn you are picking, and then you look at the probability of picking a red ball, then you can compute the total probability of picking a red ball in this experiment. So, that is where this is useful, and it does not have to be it can be a countable, it does not even have to be a finite set of urns, it can have a an countably infinite set of urns, right. Okay. This property okay? Any questions? Number 2, property number 2, let A belong to F with probability of A greater than 0 and B I equals 1 2 dot 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 B as in 1. So, by B I as in 1 I mean that B I's are a partition of the sample space with each having positive probability. Okay. Then probability of B I given A is equal to probability of A given B I times probability of B I divided by sum over J probability of A given B J times probability of B J. Okay. So, notice that now I am computing, I am not computing probability of, so I am not starting with probability of A given B, right, I am computing B I given A, right. So, on the right side of a vertical line I have A now, so I should ensure that A has positive probability, but all over here I have the BI's, the BJ's are on the right of the vertical line, so they should all have positive probability. Okay. So, then I have this relationship. Okay. This is a property. What is this called? Bayes' rule. So, it is a very trivial, actually it is a very trivial identity. If you this what is in the denominator is P of A, right, by the law of total probability. So, you bring this here, it becomes what? It will become probability of B I intersection A, and this is also probability of B I intersection A. So, you are just writing P of A intersection B in two different ways, right. So, there is really very little to Bayes' rule, it is not some very it is a very straightforward application of the definition of this conditional probability. Okay. It looks big because you are applying total probability in the denominator. So, you bring this here, it will become probability of B I intersection A, which is also the numerator, right. Okay. So, in the urn and ball example, so you are looking at the probability of, so given that you got a red ball, what is the probability it came from urn number I, right. So, given you are picking from urn number I, you know the probability of a red ball, but so post facto you are telling, oh, I got a red ball, meaning A is the event that I got a red ball, oh, I got a red ball, but what is the probability that I got it from urn number 27, right. So, this is called, because you are asking this post facto question, this is called a posteriori probability. Okay. A posteriori just means that after the fact, okay, as opposed to a priori, which is means prior, right. Yeah, so this you can compute, there are lots of examples you can compute this for. Okay. So, but mathematically it is a very simple application of conditional probability definition. And finally, I will put down one property, the property number 3. let a I in f I equals 1 2 dot dot dot, then probability of intersection I equals 1 through infinity a I is equal to probability of a 1 product so intersection j equals 1 through I minus 1, okay, intersection blah 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 a j, okay, as long as the conditional probabilities are defined. Okay. So, I am considering the probability of a countable intersection now. Okay. So, this is the probability of the countable intersection of a bunch of events. I am writing it in terms of a conditional probability, product of a bunch of conditional probabilities. So, why have I said as long as the conditional probabilities are defined? I have to have, see, each thing that I am conditioning on here must have positive probability, right. How do you prove this? Yeah, induction. So, when can you use induction? When you are proving a statement about the natural numbers, right. Induction is always used to prove a statement P n about natural numbers, right. Is this a statement about natural numbers? No. So, you cannot use induction. So, you have to use continuity of probabilities. Okay. So, what you can do is LHS, proof LHS is equal to, by continuity of probability I can write this as limit n tending to infinity probability intersection I equals 1 through n a I, correct, continuity of probabilities, yes, and now I can use, so now this is a finite intersection, right. So, I can write this as, I can keep the limit and write this is probability of a 1 times product I equals 2 to n all that, right, all that, right, and then if you, and then you are sending n to infinity in the product, right. So, that will become this, okay. You will get, so you are just taking p, so for n equal to 2 you will have a probability of a 1 times probability of a 2 given a 1. So, if you had 3 for example, it will have a 2 given a 1, probability of a 3 given a 1 intersection a 2, right, that is just by definition, right. So, you just figure this out, okay. But the key step I want to emphasize is the continuity of probabilities, that is the key step, right, everything else is just definition of conditional probability, Okay. Yeah, so this just says that if you know a bunch of finite conditional probability, so this is all A given a finite intersection, right, then you can compute the probability of this countably in finite intersection. Okay. Okay. Any questions? Okay, if there are no more questions on conditioning, I will go to the next topic. Okay, it's a very short topic, this conditioning. The next topic is a very important topic. Independence. Okay. So, talking about independence of events. Okay. So, as usual, you are given a probability space. Okay. So, this independence of events is defined as follows. Okay. First, we will define independence of two events, and then we will go on to define independence of arbitrary collection of events. Okay. Events A and B are said to be independent under P. Or simply independent when the measure P is unambiguous. Measure P is if probability of A intersection B is equal to probability of A times probability of P. So, you are given two events, right, A and F are A and B are both elements of F. Okay. You say that A and B are independent under measure P, under the probability measure P, if probability of A intersection B is equal to probability of A times probability of B. Okay. So, the reason I have said independent under P is because if you have some other measure on it, like some P prime is another measure on omega F, the same events A and B may not be independent, right. So, two events A and B may be independent under some measure P on this probability space. If you put some other measure on it, they may not be independent depending on what that measure is, right. So, strictly speaking, you should say A and B are independent under that particular probability measure, right. So, what I am saying is whether or not two events are independent depends on the probability measure, but what, so here I am clarifying that we will only say they are independent as long as it is very clear what probability measure we are talking about. So, every time I will not be saying, oh, it is independent under P, right. So, if it is very clear what probability measure I am talking about, if there is only one measure or it is completely clear, then I will not keep saying under this particular measure, okay. I will just say independent, that is it, A and B are independent. So, it is actually a very simple definition. If the probability of the intersection of two events products out into the probability of A times probability of B, then A and B are said to be independent events, okay. Now, this is the definition and this is the only definition, okay. So, do not take any other notion you may have of independence from now on, okay. So, you may have some intuitive meta understanding of independence of events, right. You may say, oh, if the occurrence of A has nothing to do with the probability occurrence of B or something like that, right. All that is misleading, okay. Do not take any of that. So, you should always say, so you should always just keep this definition, probability of A intersection B is equal to probability of A and probability of B, then A and B are independent. So, this is the definition. So, if probability of B is greater than 0, note that if A and B are independent, then probability of A given B is equal to simply probability of A. Okay. If probability of B is bigger than 0, okay, then probability of A given B is simply equal to probability of A if A and B are independent. So, why can't we take this as the definition of independence? Because this is not even defined if probability of B is 0, right. So, this is the thing to take, right, and if probability of B is greater than 0, then this is true, but this is a consequence of the definition, okay. This is not the definition, okay. Yes.
By definition, if there is only if or if and only if is also there.
So, a definition always has if and only if, you can think of it that way, okay. So, definition there is no need to say if and only if, only in theorems you say if and only if, right, to prove two directions. See, you do not know what independence means, right, you have not even heard of it so far, let us say. I am telling you what it is. Definition is what something that tells you, right. You say that two events are independent if the probability of the intersection is equal to the product of the unconditioned probabilities. So, the reason that I cautioned you about taking this definition and only this definition is because many students have some intuitive understanding of independence, which can sometimes get you into trouble, right. So, you can say, oh, the occurrence of, let us say A and B are independent, if people often say if the occurrence of A does not reveal anything about the occurrence of B, right, things like that, it is not true, okay, all that is not correct, okay. I want to make that perfectly clear. All those kind of intuitions hold if only both events have positive probability, okay, that intuition that, oh, the occurrence of A says nothing about the occurrence of B, whatever that means, that intuition is actually a wrong statement, because for example, let me give you an example. Let us say that you are working with 0, 1 Borel and Lebesgue, our favorite measure, right, 0, 1 Borel Lebesgue. Let me say A is the event of a rational, let me say B is the event of a irrational, okay. Are they independent? A is the event that it is rational, B is the event that it is irrational. So, probability of A intersection B is null, right, there is no number which is both rational and irrational. So, this will be 0, and what about this? Will also be 0 because probability of rational is 0, right. So, if I ask you, oh, I throw a dart on the 0, 1 interval under the uniform Lebesgue measure, under the Lebesgue measure, is the event that it is a rational independent of the event that it is an irrational? The answer should be what? Are the two events independent? Yes, right, because that is what the definition says. But if you go by but if I know that if I know that the dart lands on a rational number, I know that it is not an irrational number, right. So, the occurrence of A straight away rules out the occurrence of B. So, it says everything about B, right. Once A is known, B is known completely, right, but still they are independent, right, which is why I am saying that you should not confuse these notions of occurrence of A, it says nothing about occurrence of B, all that is misleading, it can get you into trouble. Okay. This is a serious matter, right, people give these kind of meta definitions very often, right. I want to urge you not to do that anymore. Okay. This is the definition. So, no, so that intuition is by and large okay if both events have positive probability. Okay. So, let me ask you a question, can an event A be independent of itself? I am taking this argument to an extreme, right. So, the occurrence of A says everything about the occurrence of A, right. Can an event A be independent of itself? If it is, if it only with null set, sample space. So, you are not applying the definition, you simply apply the definition, right. So, I am saying that A is independent of A, then I have to say probability of A intersection A equal to probability of A times probability of A, which means P of A is equal to P of A squared, which means P of A should be 0 or P of A should be 1, right. Can you say anything more? You cannot say that A should be null or A should be sample space, not true, not true, because A can be Cantor set or something under the Lebesgue measure, right, or A can be irrationals, probability is 1, right. So, the even under the Lebesgue measure the probability of getting an irrational is independent of itself, right, that is true. Okay, there is nothing fishy going on, it is actually true, right. So, that is I want to caution you against these kind of folk definitions, they are not correct. Okay, this is the correct definition.